Last class, we were working on titrations and equivalence points. And we were looking at things primarily that weren't using indicators. And we were looking at what happens if we add a little bit of our acid or base, depending on what we're titrating, and how the pH changes throughout that whole process, and so on and so on. And then we got to fun stuff like titration of a weak acid with a strong base. We had previously covered strong acid, strong base. So this is a slightly different scenario. But overall, not too much changed, just that we got the added bonus of having a conjugate base, the conjugate base of our weak acid, and so that is also a weak base. And so that's going to mean that our equivalence point is not pH neutral. In this case, we found that it was 8.22. And when we add more strong base, then the strong base is going to overwhelm the weak base, and the calculation is the same as for a strong acid, just because our strong base takes over, and so our weak base, the conjugate base of our weak acid, is not really contributing anything meaningful. So after equivalence point, strong base is way more concentrated or way more influential, has way more effect. How about that? Strong base has way more effect than the weak conjugate base. So the only time really that things are different is at the equivalence point, mostly. If we continue on with a couple more data points at 5 milliliter increments, that finishes out this top end of our curve. And these are more calculations that you could do if you wanted to, but to save time, we're going to skip them. You can see as we're adding more sodium hydroxide, right, our pH continues to go up, but not by a very large amount, because we've already got a relatively large amount of sodium hydroxide. The biggest change was when we were first kind of starting to have a sodium hydroxide dominated solution. After that, we're just adding a little tiny bit. It's kind of diminishing marginal returns, but for pH. So this is typically what a titration of a weak acid with a strong base would look like if you plotted out the data points. You'll get some a little bit of wiggle in terms of where this equivalence point is left and right, depending on how concentrated it is. And the equivalence point is also going to scoot up or down a little bit, depending on the weak acid that you're using. The weaker the acid, the stronger the conjugate base. The stronger the conjugate base, the higher this equivalence point is going to move. So we'll have a higher pH equivalence point, with stronger conjugate base. Higher pH at equivalence with a stronger conjugate base. So weaker acids will have a higher pH. Okay, a calculation. A 40 milliliter sample of 0.100 molar nitrous acid is titrated with 0.200 molar potassium hydroxide. Calculate the pH at the equivalence point. We are given a Ka value. What is this Ka value for? What chemical? What does the A stand for? The A stands for acid. What acid do we have here? Nitrous acid, HNO2. So that's for HNO2, should be two directional arrows. The equilibrium of HNO2 with its dissociation. It's the acid dissociation constant. So that's the Ka for that process. We're also given a volume of our nitrous acid, and we're told that it's titrated with potassium hydroxide. So the first thing that we're going to want to find is how much potassium hydroxide did we add? So to figure out how much potassium hydroxide we've added, we have a monoprotic acid and a monobasic base. So those are going to combine in a 1-to-1 ratio. So we don't have to worry about our stoichiometry. We just need an equal number of moles of acid and base. So 40 milliliters HNO2 times 0.100, I'm going to use that millimole per milliliter trick here. We learned that last class as well. So the milliliters cancel, and we've got the number of millimoles of HNO2. That's going to be the same as the millimoles of KOH because it's a 1-to-1 ratio. And we've got our molarity of our potassium hydroxide. So we can figure out how many milliliters of potassium hydroxide we'd have to add. Then our millimoles cancel. We're left with 20.0 milliliters. Why did we need to figure that out? The reason we needed to figure out this volume is this volume of 20 milliliters is going to be added to the 40 milliliter volume. We're going to have 60 milliliters in our flask. That's going to change our concentration of the NO2 that's produced. And we're going to be using an ice table, and we need to use molarity in an ice table. So that's why we had to figure out this volume first. So the ice table that we're doing is to calculate the concentration of hydroxide. We're going to have NO2 minus floating around in solution. That's going to behave like a weak base. So we'll have hydroxide and we'll have a little bit of nitrous acid also reforming. Those are the things that show up in our Kb expression. anytime that we're working with an ice table, we need the units in molarity, or if we're working with gases, atmospheres. Our initial concentrations of hydroxide is going to be approximately 0. It'll just be the water dissociation amount, which is really small. We can ignore it. We're going to have 0 of the HNO2 to figure out how much NO2 minus we have. That's why we were doing this, figuring out the 20 milliliters. So 20 milliliters plus 40 milliliters, 60 milliliters of solution, and we've got 4.00 millimoles of NO2 minus. So we'll end up with 0.066-ish, 2/3 of a hundredth molar NO2 minus. Put a little hat over the second 6 because that should be repeating. All right, 0.066 repeating for our NO2 concentration initially. Initially, we have none of the HNO2 in solution. That means that this little equilibrium expression that I wrote out can only move in the right direction. So we're going to have our negative x plus x plus x that we have seen so many times before. And we need somewhere to put these x's. Where can we put our x's? Texas? It's a dumb country song reference. Who knows where we can put the x's? What do we do with them? An equilibrium expression. What do we call our equilibrium expression for this? K something. K sub what? We've had Kc, Kp, Kb, Ka, Kw. Previously, we've seen Keq. What kind of chemical is NO2 minus? How is it behaving here? Is it behaving like an acid or a base? It's behaving like a base, so what we're looking for is Kb. That would be our label for what we've got here. And it's going to be the concentration of hydroxide times the concentration of HNO2. Might also be seen as HB plus. And then on the bottom, we'll have concentration of NO2 minus, which might otherwise be shown just as B for weak base. Okay, so we've got a place to put our x's. We, however, do not know what Kb is. So we'll need to figure out what Kb is. So we get x times x over, kind of looks like a face, 0.066 repeating minus x is equal to Kb. We have Ka, so we can find Kb. So Ka times Kb equals Kw. we're just going to assume that we're at 25 degrees Celsius. So 1 times 10 to the minus 14 divided by 4.6 times 10 to the minus 4. Write it out here for us. We get 2.17 dot 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 times 10 to the minus 11. And now we have a wonderful opportunity to use our favorite little shortcut. X is small. We can assume that X is small because our concentration is, close-ish to 0.1, and our KB is 10 to the minus 11. That's super small. So it shouldn't have any bearing on the result that we get. But you could always do the equilibrium method with a polynomial solver instead, and that would let you know for sure. Okay, so we end up with x squared equals 2.17 dot 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 times 10 to the minus 11 times 0.066 repeating. We'll square root both sides. That will give us x. So 1.204 times 10 to the minus 6. And that is also, since that is x, going to be our concentration of hydroxide according to our table. It's also going to be our concentration of HNO2. So there's two different ways you can solve this. They get you approximately the same answer. One of the ways that we can solve this is we have now a concentration of our weak acid and a concentration of our weak base. It doesn't really change. It's still going to be this 0.06 repeating. And we have a Ka value, so we could use Henderson-Hasselbalch. We can also just jump through a couple of hoops with POH and change that into pH. So our POH, 5.919 dot dot dot, 14 minus POH equals pH. And we end up with a final result of 8.08. So a lot of the little steps that we've been building up over the last couple of weeks, kind of cumulatively stacking up, arriving at this. I wouldn't exactly call it a whopper of a problem, but there are a lot of steps. A check to see if we did things correctly. We're doing a titration of HNO2. HNO2 is a weak acid, so its conjugate is a weak base. We should have a little bit of weak base at equivalence point. A weak base means that we'll have a little bit of pH elevation. It'll be slightly basic. A pH of 8.08 is slightly basic, so probably did things right. I plugged in my, when I was running through this last night, my Henderson-Hasselbalch, I plugged some of the things in wrong and I ended up with a negative pH. So my brain was like, nope, that's definitely wrong. We did not end up with a negative pH at the equivalence point. Questions about any of those steps?
For the ice table?
Yeah.
Why didn't you put the 0.100 molarity HNO2?
So I didn't exactly skip the first step, but this whole bit in green and the top section here in red, that was setting up getting to the equivalence point. So we could have done a stoichiometry table first. We've seen some of those in the previous slides, we could have done one of these, right? So this was what I was doing with that green and then that top right corner of the red text. So we get to the equivalence point, and then that's our new initial point. And then we're calculating what's our pH based on our conjugate base. Other questions? All right. 2 25 milliliter samples of unknown monoprotic weak acids A and B are titrated with the same concentration of sodium hydroxide solution. The titrations are shown below, which is more concentrated and which has the larger Ka. Give you a little bit to think about that. All right, which of the two solutions is more concentrated? It's A?
I thought it was B too.
Why did we think it was B?
Because you need more NaOH to reach the equivalence point.
So our equivalence point in A, right, is somewhere like there. And in B, it's like there. So for A, it's almost 35 milliliters, whereas for B, it's under 25 milliliters.
If we looked at the curves instead of where the pH was. Or where how much ml was that in?
So that would be what we would be looking for which is more concentrated. So A is more concentrated. And then which has a larger Ka? How is a Ka going to affect the way that our chart looks? Our graph looks. We've got a weak acid. When we're at our equivalence point, we're going to just have weak base. The strength of our weak base will change something. I think there's another way that we can figure this out as well. I think the other way is better. Any ideas? Yes?
Will it change the pH?
It will affect the pH.
So is it acidic?
So there's two approaches, two things that are coming to mind. The one that I think is the more helpful, which I'm a little sad that I wasn't thinking about the other times that I've looked at this, is our Henderson-Hasselbalch equation. There's a point where this will become useful, this pH equals pKa plus log concentration A minus over HA. That point is going to be at the half equivalence point. at half equivalence point, concentration A minus equals concentration HA. So pH equals pKa, which is neat. So that would be one way to solve this. And if our milliliters added at the equivalence point for acid B is around 24, then we would be looking at about 12. For our half equivalence point, for the 34-ish for acid A, we'd be looking at about 17-ish. For our half equivalence point, so half equivalence points in red. And we would be trying to compare those two values. And for acid A, our pKa is approximately maybe 5.7-ish is what it looks like to me. We're a little bit below 6. For acid B, our pKa is approximately 4.6-ish. And that correlates with a larger Ka. You can do 10 raised to the negative pKa, and that one will be slightly bigger. They're both really small, but that one's bigger. The other way that we can solve it, which is a little bit less satisfactory because it's a little harder to read, in my opinion, is what one of our suggestions was. It'll affect pH. So at our equivalence point, if we have a larger Ka, that means we're going to have, it feels early even though it's not. Larger Ka means a stronger acid. Which means weaker conjugate base. So lower pH at equivalence. That's what my brain was trying to get out and explain. So we can also compare the pH at the equivalence point, which is a little bit harder to see on just the regular non-derivative plots. For acid A, it does look like it's maybe around 9. For acid B, it looks like it's below 9. Maybe a little below 9, to me at least. I think the half equivalence point method, you'll get a better read on which is stronger or weaker in terms of Ka value. Aside from my brain resetting in the middle there, any questions? It's a lot of concepts to keep track of. Okay. We can also do titrations of a weak base with a strong acid. It's going to be similar but kind of opposite. So we're going to start basic, and then the equivalence point will be acidic because we're making a conjugate acid at the equivalence point. That'll be kind of what dominates in the solution, and then as soon as we add a little bit more acid, that's going to take over, and then it's just the normal acid behavior. We can also use the half equivalence point to find pH, and pKa for the conjugate acid. We can do stuff with that in there as well with our Henderson-Hasselbalch. Let's say that we are doing the titration of a weak base with a strong acid, and the pKb of our weak base is 8.75. What is the pH at the half equivalence point? We've got a guess for C. Any other guesses? The correct answer here is C. Our pKb is 8.75. Henderson-Hasselbalch works for pH and pKa. And when we're at the half equivalence point, that log term turns to 0 because it's log of 1. So pH equals pKa at the half equivalence point. So we need to figure out what our pKa is. pKa plus pKb equals 14. So pKa equals 14 minus 8.75, or 5.25. If we have a polyprotic acid, like phosphoric acid that we did last week, we have a couple of, or 2 weeks ago, we've got a couple of equivalence points. If they are sufficiently different, if they're a significant volume different from each other, then we'll have equivalence points, or 3, or however many we have. The volumes needed to reach each of the equivalence points are identical, because we need to have a mole equivalent. So for every mole of our acid, we would need 1 equivalent of our base to reach an equivalence point, and the moles of our conjugate base, when we pull off one of those protons, we're going to have the same number of moles, and so we'll just need 1 more equivalent to pull off that next proton. So we'll have the same mole of acid. Yeah. Same moles of acid. So like if we have 10 millimoles of H2SO3, then to get to the first equivalence point, let's draw this here at the start. So initially 10 millimoles of H2SO4. After we add 1 equivalent equivalence of base, that's going to pull off 1 of the protons. Then we'll have 10 millimoles of HSO3 minus. To pull off 1 of those equivalents, we just need to add 10 millimoles of the next thing. So that's why our equivalence points should be evenly spaced out. If your Ka values are really close to each other, then you might not get spacing, you might not be able to see them, which I'm assuming is what's happening with that phosphoric acid third equivalence point that we didn't see 2 weeks ago. considering 3 titrations, it's all the same volume, the same concentration, and titrated with the same concentration of base. In titration 1, we have a monoprotic weak acid. Titration 2, we have a diprotic weak acid. In titration 3, we have a strong acid. Which of the following statements is most likely to be true? All 3 titrations will have the same initial pH. All 3 titrations will have the same pH at their first equivalence points. Or all 3 titrations require the same volume of sodium hydroxide to reach their first equivalence points.
Is it B? Is it A? Or C?
It's C. So let's think through statement A. All 3 titrations have the same initial pH. So before we add sodium hydroxide, the pH of these 3 solutions, we've got the same amount, same mole amount, same volume, same molarity, whatever, of each of these things. We've got a monoprotic weak acid, so that's going to be slightly acidic. We've got a diprotic weak acid, probably also just slightly acidic. And then we have a strong acid, which is going to have full dissociation. So that's going to be our most acidic for sure. That'll probably be a pH of 1. So strong acid pH is lower than weak acid pH, since the weak acid doesn't completely dissociate. So it's not A for those reasons. For B, all 3 titrations have the same pH at their first equivalence points. They'll probably all have different pHs at their first equivalence point. We know for 3, since this is a strong acid, at its equivalence point, the conjugate base of a strong acid is pH neutral. So for 3 will be pH 7. For titrations 1 and 2, these are both weak acids, so the conjugate base that we'll be forming is going to be a weak base rather than pH neutral. And so those will be slightly basic. Number 3 is, or number C, letter C, is the correct answer here because we've got the same volume and the same concentration, so we have the same number of moles or millimoles of our weak acid, our diprotic weak acid, and our strong acid. So we just need to add that same equivalent amount of our sodium hydroxide to pull off that first proton. So that's because we have the same moles of each acid. All right, indicators indicate. Indicators are pH-dependent markers that we can put into our solutions. The one that you've used before, probably phenolphthalein. Indicators are nice because if we're doing the same titration over and over again, or we just don't have the tools to set up a pH meter, or we just don't want to bother with a pH meter, an indicator can be a really nice way of telling when we're at our equivalence point. So with our indicators, we rely on the color change. Oftentimes it'll be the first color change. Because some of them will have multiple colors that they can do. to determine our equivalent point. But it also depends on like the acid or the base that you're using. And if we set it up correctly with the correct indicator, our endpoint is going to occur at the equivalence point. For phenolphthalein, it is the first sign of color change before our color gets saturated. So we've got a phenolphthalein titration here, our volume of base added on the x-axis, our pH on the y-axis. We've got an acidic solution initially. We're adding base, we're adding base, we're adding base, and then it spikes suddenly as we're close to our equivalence point, and that's when we see this light pink color change, because just some of our indicator has converted to a color form. And then as we add in more base, the color gets saturated because all of our indicator has changed color. Our indicators are weak organic acids that have a different color than the conjugate base. So this is phenolphthalein in its colorless form. So this is in acid solution. And in a basic solution, it's a pink color. So these groups change. There's also this linkage that changes. There's a couple of changes that happen when we put this into a basic solution that cause it to restructure and absorb light differently or interact with light differently to turn that pink color. The indicators change color within a range of 2 pH units. So plus or minus 1 pH unit centered at their pKa. IN here is indicator. The indicator is conjugate base. And HIN is indicator. And we can get a couple of different colors. So looking at this one here on the right, this is methyl red. And at different pHs, the color is different.
Are we going to need to memorize like the different color indicators?
No, you do not need to memorize the indicators. This is some of the indicators. So a few that are popular, phenolphthalein is a big one. That's the one that we've done before. You've probably done before. Bromothymol blue is another one that's popular, you may have heard of. I would guess that probably most of these other ones. I've heard of crystal violet as well. Yeah, thymol blue. I think bromothymol blue or bromthymol. I don't know if they're supposed to zero there. Yeah, so some of these are relatively common. But no, you don't need to have these memorized. You would be given information about these. Realistically, I'm probably not going to test you on like maths for indicators. It would just be like a concept question, maybe. All right, now on to more fun stuff. Arguably, solubility equilibria is slightly easier than a lot of the other equilibria stuff that we've been doing, which is great. In some other ways, though, it is confusing. So we'll talk about that. We have looked at solubility rules in the past, and by we, I mean possibly you and I, but more likely you and someone else. So classifying different ionic compounds as soluble or insoluble. There is a green sheet handout that you may have that has a solubility table, and for the most part we've just been saying yes, it's soluble, or no, it's not soluble. But now we have the tools to examine the extent or the degree of solubility. So we can look at how much of something is dissolved or how little of something is dissolved, since dissolution or dissolving is an equilibrium expression. And you may remember this solubility product constant, KSP. It's a measure of the solubility. It's expressed the same as our other K expressions, but for all of our KSPs, we're going to have a solid as our reactant. And since it's a solid, we omit it, so it's just the products, the different ions that are the products. And this 2, for example, comes up and becomes the exponent of 2 for F minus concentration. So it's like Kc, but the reactant is solid, so we omit it. We can calculate molar solubility, which we'll usually represent with S. So we're going to do ice tables, spoiler alert, but we're going to use S instead of X, because S stands for solubility. And we can measure our solubility in moles per liter or molarity. We can calculate it from KSP, but KSP is not the molar solubility. They are different. So S is solubility, KSP is solubility product constant. And we can also have, a little foreshadowing here, different values in different solutions for molar solubility thanks to the common ion effect. So if we already have some of that ion dissolved in solution, that's going to shift our equilibrium a little bit away from that, so we won't dissolve quite as much. It involves an equilibrium calculation. Let's take a look at that equilibrium calculation. So considering AgCl silver chloride, we have a KSP value of 1.77 times 10 to the minus 10, nice and small. Initially, we have no silver and no chloride ion in solution. So our initial, 0. Since there's nothing dissolved, some of it's going to dissolve. So our change is plus S. And so our equilibrium values are just S. We can write out an expression for KSP, concentration of silver ion times the concentration of the chloride ion. So KSP equals S times S, because at equilibrium, that's what those concentrations are going to be. So that is S squared. So S, skipping a step here, equals the square root of KSP 1.77 times 10 to the minus 10. So our S here, our molar solubility, 1.33 times 10 to the minus 5 molar. Depending on who you took 3A with, you might have also covered this sort of a thing with them in 3A, just without the ice table. And there's a lot of solubility product constants. For anything that dissolves to some extent less than completely, you're going to have a KSP. You also don't need to memorize any of these KSP values. They'll be given to you, but this table might be helpful for you when you're doing homework or something. Let's do another one. Calculate the molar solubility of iron 2 hydroxide in pure water. So this time, molar solubility of FeOH2. Our KSP is given to us. We can write out an ice table. In solution, we are going to form iron 2 plus. We are also going to form hydroxide. Initial change equilibrium. Initially, we have none of either of those. When they dissolve, we're going to add a stoichiometric amount of each of those. So it might be helpful for you to write out your dissolution equilibrium expression. This. Fe2 plus 2 OH minus. You don't necessarily have to write this out if you can just see it, that that's what we're going to get in your head. Otherwise, writing out that expression, the ion dissociation equation, whatever, might be helpful. Okay, so our changes, we've got no iron or hydroxide initially, so we're going to be gaining these. For iron 2 plus, we're going to be gaining S. We've got an invisible coefficient of 1 on there. For hydroxide, we have a coefficient of 2, so we're going to be gaining 2S. We'll have twice the concentration of hydroxide compared to our iron 2 plus. So at equilibrium, we'll have S, and we'll have 2S. And then we need to do our KSP expression. So our solubility product constant expression is going to be what? Concentration of?
Fe times OH.
Concentration of Fe2 plus times what?
OH minus squared.
Concentration of hydroxide squared. This is the tricky twist. We've been looking at plus x minus x so much. So this is the little tricky twist. We plug in our S and our 2S, respectively, for Fe2 plus and OH minus. KSP equals S times 2S squared. That's the tricky part, is remembering to put in 2S to this thing that's squared. Otherwise, you'll be off by at least a factor of 2, if not more. So that'll shake out to 4S cubed. Skipping a little bit of the algebra, S cubed equals KSP over 4. And we can undo the cube with a cube root. So S is equal to the cube root of KSP over 4. you should have, if you don't know how to access a cube root, you should have this function, the square root thing, but with a little box there. You just need to make sure you put a 3 into that box. And you should get 2.30 times 10 to the minus 6, if the math is correct. Questions? Okay. The molar solubility of silver bromide in pure water is 7.3 times 10 to the minus 7. Calculate KSP. I will give you a little bit of time to work on this one. Okay, that was a very short amount of time. Let's go through it. We have AgBr, a solid. That's going to dissolve in water to some small extent. It's going to form Ag plus and Br minus. Both of those would be AQ. Our ice table doesn't matter. Oop. We don't really need an ice table here. We just need a KSP expression. KSP equals concentration of silver ion times concentration of bromide ion So our KSP, we plug in that 7.3 times 10 to the minus 7 for both of those. And it'll be like 5 times 10 to the minus 13. Oh, look at that. There's our KSP. Questions? You might have to do an ice table if it's not a one-to-one, or you might want to do an ice table if it's not one-to-one. Strictly speaking, you don't have to do an ice table. But since it's one-to-one, it works out nice and easy. All right, now on to the fun stuff. Fun-er stuff soon. So molar solubility, S, and KSP are related, but if we have two different compounds, we can't use them to directly compare the two. So let's look at magnesium hydroxide and iron 2 carbonate. Their KSP values, magnesium hydroxides is lower than iron 2 carbonates, FeCO3s. So lower KSP, but the way that the maths works out, our solubility for MgOH2 is actually higher than for FeCO3. And that's because of the two hydroxides and the magnesium hydroxide. So we have slightly different KSP expressions, and so that's going to make our solubility not line up the way that we do. The relationship between KSP and molar solubility depends on the stoichiometry. So if we have something that is the same like type of compound, so these are both of the form metal and two other things, magnesium hydroxide and calcium fluoride, their KSPs have this relationship. The solubility is also in that same vein. So higher KSP, larger KSP for calcium fluoride, larger solubility, smaller KSP for magnesium hydroxide, smaller solubility. So if they're the same type of thing, if you can break them down this way to be the same thing, then we can make predictions. Otherwise, we'd have to do some math. So this is where we get into the fun stuff, common ion effect. The solubility of an ionic compound, those compounds we've been looking at before, is lower if there's a common ion in that solution. So looking at dissolving calcium fluoride into water, if we already have fluoride in the water, that's going to slightly shift our equilibrium to the left. It's not going to be pushing to the left. It's going to be just shifted a little bit to the left because we don't have any calcium ions in solution. So it's still going to dissolve. It's just not going to dissolve quite as much because we have the fluoride there. So the fluoride, I'll just write F minus. The F minus present in solution inhibits, restricts the dissolution of CaF2. CaF2 dissolves less because of F minus present in solution. They're saying the same thing. I think the left one's just a little friendlier. All right, so this is where our equilibrium stuff gets a little bit more interesting. We want to calculate the molar solubility of calcium fluoride in a solution containing 0.250 molar calcium nitrate. So what we're looking for here is, do we have a common ion? So do we have a common ion? Yes, we do. We have calcium. So calcium is a common ion. So that's going to be our initial amount for calcium nitrate. Calcium nitrate should be completely soluble because of the nitrate. So our ice table, we're going to have calcium, we're going to have fluoride. Our initial for calcium, 0.250. Our initial for fluoride, 0. Our change values we are still going to be dissolving some of our calcium fluoride because we don't have any of the fluoride present. So it's still going to dissolve, just not quite as much. And for the fluoride, this is where it might be helpful to have your little dissolution equilibrium expression. So CaF2 in equilibrium with Ca2 plus and 2F minus. Strictly speaking, you don't need to write one of those, but it could be helpful. So because of this 2 in front of our fluoride, we're going to be adding 2S for our fluoride. Then our equilibrium amounts are our initial concentration of calcium plus S and 2S. And we need to write out a KSP expression, solubility product constant expression. Concentration of calcium ion times concentration of the fluoride ion squared. You tracking? Okay. So we'll plug in our equilibrium values for the KSP here. So 0.250 plus S for our concentration of calcium, and then for our concentration of fluoride, 2S, and that whole thing is squared. You can maybe see that this is going to end up being somewhat of a mess, unless we invoke our old friend, x is small. In this case, it's s is small. It's basically the same thing. We just have a different variable. So we invoke our old friend x is small to get rid of that plus s, and suddenly things look a lot more palatable, a lot more manageable. We don't need to do quadratics big brother where we have x cubed. All right, so this will shake out to 1.46 times 10 to the minus 10 equals, we're going to have this 0.25, 1/4. This 2s squared is going to turn into 4s, so it's just s squared that's left over because the 4 and the 0.25 will turn into a 1. So I'll write a 1 in there, and then s squared. So s is equal to square root 1.46 times 10 to the minus 10 and our answer is 1.21 times 10 to the minus 5 molar. Questions? All right, we'll stop there. Actually, no, let's stop here after this one because this is not a calculation problem. In which solution is barium sulfate most soluble? A solution that is 0.1 molar barium nitrate, a solution that's 0.1 molar sodium sulfate, a solution that's 0.1 molar sodium nitrate. A, B, or C? It's going to be C. In A, we have a common ion. That will restrict or reduce the amount that it dissolves. So common ion reduces solubility. And in B, we have a different common ion. So this common ion reduces solubility. And in C, we have no common ions. So we'll have the highest solubility in C. And we'll pick up after this slide on Wednesday.